Syndesmoscope is a network visualization system that combines traditional network views with invariant plots. The interface shows four linked views of the same network. Let's start our walkthrough with the Game of Thrones dataset, where nodes are book characters and edges are spoken interactions. The first pane shows our new K-snakes plot, where dense nodes are at the top and sparse nodes at the bottom. This follows the K-core decomposition of the graph. Here we see 7 shells stacked vertically. Within each shell are subshells, which come from nodes that are connected within the shell. Inside each shell, nodes zigzag by onion decomposition. The subshells line up with the connected components we see in the force-directed view on the right. Now let's open our second view, the hop census pane. In this example, the top bin holds a single polyline. This polyline is the most central node of the graph. In contrast, the bottom bin has many polylines. These are the nodes on the perimeter of the graph. In K-snakes, we see that some of these are leaf nodes, in the sparse K1 shell at the bottom, but other nodes belong to denser shells, like K4, and some outbound edges reach all the way up to K6 near the top. Both the K-snakes pane and hop census pane are invariant plots, which means that their visual patterns come entirely from graph topology. Now let's open our third pane, the adjacency matrix pane. We've rotated the matrix so the diagonal runs vertically. This makes it easy to select the top and bottom parts and see the clusters in the force-directed view, which is our fourth pane. Each of the first 3 views has its own geometric layout, and each vertical axis reveals a different aspect of topological structure. We've been selecting elements in one pane and seeing how they look in the others. We call leapfrogging this form of linked highlighting. Let's switch to a simple square grid. This well-behaved case will help us understand how the views work. We select the K-snakes bins from top to bottom. In hop census, the highlighting follows from top to bottom as well. Here, density and eccentricity line up perfectly. The dense shells contain the central nodes, which have the lowest eccentricity. In the force-directed view, these nodes sit right in the middle of the layout. In this symmetric graph, the 2 poles in the adjacency matrix view are 2 opposite corners of the grid. When we select the equator, we see a band stretching between the other 2 corners, equidistant from the poles. Now let's look at the hopscotching interaction in more detail. Let's switch to the Wikipedia Science Pages graph. We start by clicking a single node near the border of the force-directed pane. Hopscotching extends selections through the underlying data structure, so we press the Hopscotch Stubs button, which selects all of the node's attached edges. Then we press the Hopscotch Nodes button, which hops outward. Then we can keep alternating between hopscotches until we have traversed the entire graph, which corresponds exactly to a breadth-first search. Now let's start hopscotching from the top bin of hop census, which has the polylines of the most central nodes. We see that these nodes form a clique. And we also see that traversal completes in fewer hops. Next, we select all of the sparse nodes of the shell at the bottom of K-snakes. These are all of the leaf nodes in the graph, which would be difficult to select with the force-directed view alone. Hopscotching from these sparse nodes traverses inward to the dense regions of the graph. Now let's switch to the fullerene graph of 720 carbon atoms. We select the long, high eccentricity polylines at the bottom of hop census. We hopscotch their shared edges and leapfrog to the force-directed view. This reveals recurring pentagonal floret motifs, which are distributed across the surface of the spherical molecule. In this example, we showcase how a single brush action can select 240 structurally equivalent nodes at once, which would be very difficult to achieve in traditional views. Let's switch to the network science co-authorship graph. We zoom into the adjacency matrix view and select the edges near the equator. These edges are equidistant from both poles. The vertical axis orders nodes by Fiedler seriation, forming a pole-to-pole spectral bisection axis. These 5 highlighted edges bridge between 2 large communities. We can drag nodes in the force-directed view to make that structure visually apparent. In K-snakes, the long orange bridge edges are easy to spot. We see a short edge between 2 nodes in the same subshell. So the mesoscale structure is slightly more complicated than a simple bridge. We can disambiguate the layout in the force-directed view by dragging nodes. Then we can see that the overlapping nodes do have an edge between them. Finally, let's switch to the Western power grid dataset, which is a large graph. We select the low eccentricity polyline bins at the top of Hopsenses. These polylines map to the most central nodes. Then we leapfrog to K-snakes. Surprisingly, these central nodes are not in the dense shells at the top. Instead, they map to the sparse shells at the bottom, which is a surprising topological anomaly. What these plots are telling us is that the topological center of this network is sparse, not dense. Then, hopscotching their shared edges shows that these central nodes are not grouped together. We can see these edges are spread throughout the force-directed view. Now let's clear our selection and select the densest shells at the top of K-snakes, and then leapfrog to the force-directed view. The selection is so small that we must dim the unselected elements to find it. Zooming in, we see that these densest nodes are actually far out on the perimeter of the force-directed view, which is counterintuitive, but indeed part of the topological structure of this particular dataset. This anomaly would be very hard to spot from the force-directed view alone, but Syndesmoscope reveals it. Syndesmoscope adapts responsively. When the window width is smaller than the height, the app layout activates a portrait mode. Also, it has both light and dark themes. In conclusion, we demonstrate how no single view of a network tells the whole story. By combining invariant plots with traditional network views, we can leapfrog between topological lenses and hopscotch through the network to discover complex mesoscale structure. You can try for yourself at syndesmoscope.vercel.app.